I'm Tim Johnson. I'll be giving the first part of the talk, and today we'll be talking about laboratory astrophysics, studying the stuff of stars in the lab. So first I want to break down just the general overview of what we'll be talking about today. So I'll first introduce the concept of laboratory astrophysics, like how do we do it? How is it even possible? And then we'll go through 4 specific examples of studies of laboratory astrophysics. We'll first talk about collisionless shock experiments at the NIF, and then stellar nucleosynthesis experiments that we've conducted at Omega. And then Jacob will talk about exploring the kink behavior of the Crab Nebula with experiments at Omega. And then he'll close with investigations of fast magnetic reconnection. So traditionally, astrophysics has been constrained to only observations, theory, and simulations. And there are a couple of drawbacks to being stuck with observations, for example. We can see just an example observation on the left-hand side of the screen here of the Crab Nebula. With observations, you're constrained to waiting for some interesting object to emerge in the sky. For example, supernova remnants only come out every 100 years or so, and you just happen to get lucky if you see one. And there are other issues with observations as well, that you're limited to only looking at a 2D projection of a 3D object in the sky. You can also only observe radiation effectively from it. So you can't use a lot of our favorite plasma diagnostic tools, such as Thomson scattering or other techniques. You're really just constrained to what you can look at and see with your telescopes. So a way people try to improve on this constraint is to use modeling and simulation. So you take your physics understanding and try to build a model out of that. This works a little bit better, but there are also problems if you're only constraining these models to these astrophysical observations. And a lot of time with the observations, you won't know what the initial conditions of the object are, so it makes this modeling step even harder. But what could we do if, for example, we could create things in the laboratory and fill in these gaps in our models and know the initial conditions of objects? So that's what laboratory astrophysics aims to do. So the laboratory is a much more controlled environment than space, and it allows for a better physics exploration and model validation. So in general, there are 2 different types of laboratory astrophysics experiments. First, on the left-hand side, we have microphysics experiments. And this is kind of the simplest, most straightforward example. So here we'll make a volume of plasma that has a very similar conditions to the astrophysical object. So if you have like the same density and temperature, for example, you'll pretty much be looking at the same exact physics. And this is applied a lot when we're studying nuclear reactions inside of the sun, for example. If we can make a little bit of plasma have the same density and temperature, we really have the same physics as what's going on inside of the sun. The other type that we do, other type of experiment is called a macrophysics experiment. And this is more of the wind tunnel approach, where you scale down the system from the astrophysical size to something that can fit inside of your laboratory. And you need to scale this well to keep the same physics relevant. So it's like if you wanted to study the aerodynamics of the space shuttle, for example, you don't need to build a massive wind tunnel or actually fly the object first. What you could do is you could scale it down to a small size and put it into a wind tunnel and do all your observations there and build a very good understanding in a much simpler system. And this is made possible by this property called scale invariance. So scale invariance is a property of the plasma fluid equations. So over on the left-hand side of the screen, we've written down the MHD equations, and the particularly troublesome terms are written out on with the x's over them. And these terms are proportional to these 1 over these dimensionless numbers, such as the Reynolds number, the Peclet number, and magnetic Reynolds number. So if these numbers become big enough, so 1 over them makes them small, we can ignore these troublesome terms, and then we get a purely hydrodynamic set of equations. And this is nice because the equations of hydrodynamics are inherently independent of global scale. So what we're able to do is take some big object in space, and if we do this well, we're able to recreate it in the laboratory and know that the same physics is going to apply. And so in general, if you want to properly scale a lab astro experiment, you need to make sure that these dimensionless numbers are similar to the dimensionless numbers that you find inside of your astrophysical system. And we'll see a couple of examples of this throughout the talk today. So we use inertial confinement fusion facilities because they let us generate plasmas for these laboratory astrophysics studies. There's two main laser facilities that we use for this work. We have the Omega Laser Facility on the left-hand side and the National Ignition Facility on the right. Omega is located at the University of Rochester in Rochester, New York, and it has a total of 30 kilojoules of laser energy and a total of 60 laser beams. And this one can fire up to 14 times per day. On the right-hand side, we have the National Ignition Facility. This is currently the world's largest laser. It has up to 2 megajoules of laser energy over 192 laser beams. And this one can fire at most 3 times per day. So just because you're going to get much more statistics by using Omega for your experiments, in general, it's more it's better to go for Omega first. But a lot of times your experiments will need to have just the huge energy scale to really get after the physics you're interested in. So that's why the NIF will be used. Okay, so now we'll change gears and talk about the first example of a lab astro experiment. And this is going to be collisionless shock experiments on the NIF. So collisionless shocks are very common in the universe. An example of one is shown on the left-hand side. We see the supernova remnant of supernova 1572, and this is an X-ray image. From observations, we know that the system size is about 10 light years across, and the highest energy X-rays are shown in purple. And you can see that there's this very thin purple band on the outside, and that's the expanding shock wave here. From other observations, we know that the plasma conditions, and we can find that the particles will travel about 1 light year before they actually experience a collision. But just by looking at the image, we see that the shock wave is much thinner than 1 light year. So this shock wave can't be pushed forward and sustained by particle collision. It has to be some other kind of phenomenon. And that's what a collisionless shock is. So instead of having their particles colliding with one another to push the shock forward and to dissipate the energy, you instead have this long scale interaction between the electromagnetic fields and the particles that sustains the shock and dissipates the initial flow energy. So collisionless shocks are interesting because they're thought to be a place of origin for some cosmic rays. So cosmic rays are these really high energy charged particles that are present in space. They bombard Earth from all directions. And we can see a characteristic energy spectrum of cosmic ray protons on the left-hand side of the screen. And we see that they go up to really, really high energies, higher than anything we can make on Earth. But the energy range of interest for collisionless shocks is going to be in the middle here. And these are called galactic cosmic rays because we believe that they come from the inside of our galaxy. And collisionless shocks are a good place to accelerate particles, in part because they're collisionless. So your particle that has been accelerated to really high energy isn't going to lose its energy through these collisions with other particles. It's going to be able to keep the energy that it has. And there are also really high and strong electromagnetic fields, and that lets different mechanisms take place on the particles, such as first-order Fermi acceleration, which can operate to accelerate these particles to very high energy. Okay, so what we can do to simplify our system some is we can zoom into this little white box here and expand to really just focus on the basic physics of what's happening. When we do this, we see that on the left-hand side, we have the supernova explosion with some velocity that's actually quite fast. And then on the right-hand side, we have the interstellar medium that it's expanding into. And this is, we'll say that this is at rest. And there's a lot of free kinetic energy inside of the supernova explosion plasma. And in general, nature really doesn't like to have this level of concentration of energy. It wants to operate to dissipate the free energy and to increase the entropy of the system. And so this system is inherently unstable to some plasma instabilities. And so these will develop to redistribute this free energy around. And so in this specific case, we'll have instabilities such as the Weibull instability growing, and this will redistribute the initial flow energy into magnetic fields. And the fields will start to reorganize the particles, and if enough time allows and if the conditions are right, a collisionless shock will form. So far we've talked about observations of collisionless shocks. It's interesting that we could actually make one of these in the laboratory. And so this was a very challenging experiment, and it had to be carried out on the NIF just because of the large length scales and time scales that were needed to make a fully formed shock. And the schematic of this experiment is shown on the left-hand side of the screen here. We have these 2 plastic foils, that are 25 millimeters apart, and we illuminate both sides with the NIF laser. And this will create these plasma flows that will expand off these foils and interact with each other in the center of the screen. If we go back to our simplified model of the supernova remnant, we see that it's pretty much the same thing here. Just imagine you split the supernova velocity between these two plasmas, or on both sides. This is just a very large system for us in the laser plasma business. 25 millimeters is quite large, so they needed to have this scale to make a fully formed shock, and that's why they had to go to the NIF to make use of that large amount of energy that's available there. So to fully understand the system, they had to use powerful diagnostics at the NIF to measure these key plasma parameters. They used optical Thomson scattering to make time-resolved measurements of the density and the temperature. And we can see that on the right-hand side of the screen here. So with shock physics, you generally expect to see an increase in the density and the temperature. That's the way that the shock has of dissipating energy and from the initial flow, and also increasing the entropy of the system. So the way that they were able to unpack this is they did an experiment where they, which is shown in the blue here, where they only illuminated one of the flows, and that kind of serves as your background. And if there was no interaction between the two plasmas as they collide with each other, you would expect only a doubling in the density and perhaps maybe the same temperature. But that's not what they see here. They see that there's this large increase in the density and a very large increase in the temperature as well. So that's giving them evidence. They're thinking that they are seeing this shock being fully formed. So the NIF experiment is relevant to astrophysical systems. On the right-hand side of the slide, we can see a table that compares these different plasma parameters between the NIF experiment and just an example supernova remnant. If you look at a few of the first entries, we see that there are very different in terms of just the raw plasma quantities. For example, the density is 20 orders of magnitude different, which is quite amazing. And system size is also 19 orders of magnitude different. But what really matters and what really constrains the physics of what's going on is these parameters on the bottom, where we have collisionality and sonic Mach numbers. The collisionality is quite similar between the two. And this is important for us to know that this is indeed a collisionless system. So if we're seeing a shock, it has to be a collisionless shock. And the Mach numbers are relatively similar. And so that's going to say that you're in a very similar region of how the shock is going to behave. Another thing that they were able to do was look for the acceleration of charged particles, and in this case, electrons. So as I mentioned before, collisionless shocks are thought to be a place where particles can get accelerated to extremely high energies. So what they did on their experiment is that they looked at the electron spectrum for just a single flow, like they did with the Thomson scattering measurements. And they get the energy spectrum shown in the blue here. And then later on, they did another experiment where they illuminated both sides and had the full interaction. And naively, you would expect if there was no shock formed or if there was no really interaction, you would only see a doubling in the number of electrons. But since this is a log-log plot, you really wouldn't be able to see that here. But instead, what they actually see is shown in the red, where we see that this goes up to, it's a lot more electrons in the medium energy range, but at high energies, it goes to much higher energies than anything they were able to see with just the single flow. So this is quite exciting to see this level of acceleration and have this additional proof and evidence of a fully formed collisionless shock. Okay, so now let's change gears again and talk about stellar nucleosynthesis experiments that were conducted at the Omega Laser facility. So inertial confinement fusion implosions use lasers to reach fusion-relevant densities and temperatures. So the target that we have for this experiment is a thin capsule. So it's basically a thin shell made out of plastic, glass, or diamond, depending on what actually you're trying to do, what physics you're after. And that will be filled with fusion fuel. And so, and for example, in some of the experiments we'll talk about, it'll be filled with just helium-3 to look for the helium-3 fusion reaction. So we take the capsule and we illuminate it on the outside with the lasers from the NIF or from the Omega Laser facility. And that is what was the lasers hit and start to interact with the thin shell. It'll create a plasma that expands outwards off of the shell. And this requires us to conserve momentum. And therefore we will have, by Newton's third law, a force that's imparted on the remaining bit of the capsule. And this acts symmetrically to compress it to very high densities and temperatures. And at peak compression, we're able to get this to be hot enough and dense enough that fusion reactions will occur. And with the fusion reactions, you'll start to see different fusion products such as neutrons, protons, or deuterons, for example. And you can look at those and you can diagnose and see what's going on inside of your implosion there. So ICF implosions can reach similar conditions to the interior of stars. We see on the left-hand side here a density and temperature space, and overlaid on that are the different trajectories of the evolution of stars. We see, for example, 1 solar mass stars and up to 40 solar mass stars. And typically the conditions of interest are going to be in this main sequence region where stars hang out for most of their life. What we can do is we can do some simulations for ICF implosions, and we can overlay what region in density and temperature space that they're able to achieve. You see that on the right-hand side, that they're actually getting to very similar conditions to the interior of these stars. So that really enables us to do these experiments and make these observations about what's happening inside of the core of the sun, for example. ICF implosions offer a better platform than accelerators to study stellar nucleosynthesis. So previously, the way that you would study a nuclear reaction that's relevant to the inside of the sun is you would use a particle accelerator, where you take you prepare your target and your ion to match the fusion reaction of interest, and you accelerate the ion to really high energies and slam it into the target. This is not a problem for high energies. If you're getting up to maybe like an MeV range, you can start to ignore the interaction between the ion and the bound electrons here. But at low energies, this is going to start to be a problem. The bound electron screening is a complicated process. It's quantum mechanical, and it's not well agreed upon how to handle that well. But the issue is that at low energies, this is the region of the nuclear reaction, the energies where this is going to be happening inside of the sun or in other stars. So this is the part that really matters the most. And we can see this played out on the right-hand side here, where we see that at low or at high energies, you have decent error bars. It kind of makes sense. Everything looks fine. But as you get to lower and lower energies, which are more important for the interior of the sun, you start to see these big error bars here. But on the bottom here, we can see that that the conditions reached by ICF experiments and the sun are very similar. We both have a hot, dense plasma. And instead of having this bound electron screening, which is a complicated process that we don't know how to deal with well, we have the more, I guess, more familiar process of device screening inside of the plasma. So you really are reaching the same physics in this case. So now I'll focus on one specific nuclear reaction that's present inside of the sun that we will be able to study inside of the laboratory. So this is the helium-3 nuclear reaction. We can see a schematic of it on the right-hand side of the slide here. It's the last step in this proton-proton-1 chain. The proton-proton-1 chain starts with just protons and fuses all the way up to the helium-3. And the last step is when we have the helium-3 fusing together to spit out 2 protons and a helium-4 nucleus. This reaction is interesting because it's responsible for producing half the energy of the sun. And it also is important in setting the initial conditions for the other proton-proton chains, proton-proton chain 2 and 3. And those reactions themselves, they produce neutrinos that have been studied looking at the flavor oscillations of the neutrinos as they are emitted from the sun. So this is an important nuclear reaction to know well, because it is going to directly affect the results of these neutrino oscillation studies, which is a pretty important area of modern physics. So experiments at Omega have measured the helium-3 proton spectrum. The results of this are shown on the right-hand side here. We see a plot of just the energy spectrum. And the experimentally observed data is shown in black here. And it goes down to the lowest energy that it can see is about 6 MeV. And this is just a limitation of the spectrometer that was used for this measurement. But we see that there's 2 theoretical models that are used to better understand the nuclear reaction, the underlying physics of what's going on inside of that reaction. And they agree pretty well with each other in the region where there's data. But once you get to the lower energy part of the spectrum, they disagree quite a lot. So we've had recent experiments at Omega to try to constrain this. And we've designed a new spectrometer that is designed to look at this lower energy part of the spectrum, as well as the high energy part, and look for this whole region. And that'll hopefully allow us to constrain our models and better understand the physics behind this nuclear reaction, and which feeds back to all these other things that I've talked about with the neutrinos and whatnot. So yeah, that's this interesting experiment here. Okay, now Jacob will talk about the Crab Nebula.
Yep, thank you, Tim. So I'll be talking about the exploration of kink behavior of the astrophysical jet that is coming out of the Crab Nebula. You can advance. So high Mach number plasma jets are fundamental astrophysical phenomenon in the universe, and it's commonly defined as well-collimated outflows coming from a compact object. So they're sort of present at a variety of different scales, as we can see from some of these observational images on the left-hand part of this slide, where they're both jets that are sort of on the galactic scale, coming from active galactic nuclei or quasars, as well as on the stellar scale, where they can come from young stellar objects, or from planetary nebulae, which are supernova remnants. So basically, a lot of the time you have some kind of accretion disk, and then sort of perpendicular to that accretion disk, you'll have these very fast jets of high energy charged particles. And some of the things that we can investigate about these jets include their generation, their interactions, and then their transport, which is what we'll be focusing on here. Next slide. So here are some X-ray images from the Chandra X-ray Observatory showing that the southeast jet in the Crab Nebula changes direction over every few years. So on the left here, there's sort of this pretty composite image of the Crab Nebula over a variety of wavelengths. And sort of the important wavelength region that we're interested in here is the X-ray, because that's what's actually showing the jet. So you can see at the center, we have the compact object, which in this case is a neutron star. And then a spinning accretion disk, and then going off either two ends of the accretion disk are these high energy jets. And you can see on the right, which is some time resolved X-ray measurements, that between 2008 and 2011, the direction of the jet changed. So while it's still sort of highly collimated along its direction, we can see that there's sort of clumping as well as directional changes along the length of the jet. So theoretical modeling and numerical simulations suggest that kink behavior, which is to say the clumping and directional changes of the jet, can be a consequence of the magnetic fields and current-driven MHD instabilities. So essentially in this model, the magnetic fields start sort of roughly parallel to the pulsar's axis of rotation, but they become twisted around the jet due to differential rotation speeds, and then they're advected with the moving jet. And ideally, we would like to control to verify this speculation in a controlled laboratory experiment, as opposed to these simulations, which are nice, but we don't really know that they accurately say what's going on if we can't confirm them with an experiment. So this particular experiment is kind of unique in that the magnetic fields are sort of the dominant thing that we're looking at, which is to be contrasted with some of these earlier experiments and their diagnostics that are shown on this slide, because these diagnostics were primarily X-ray and optical, and the photons produced by X-ray, or the photons, are essentially not sensitive to magnetic fields. So we needed a diagnostic that would allow us to detect those fields. But yeah, so the diagnostics that are shown here include X-ray backlighting, where X-rays are simply sort of sent through the plasma and they give you some idea of the density where they don't propagate, or X-ray self-emission, which is just where the plasma itself is hot enough and dense enough to produce these X-rays, or X-ray interferometry, which also gives sort of an idea of the density. Or on the right here are optical self-emission, which is basically the same thing as the X-ray self-emission, just not as hot. So to mimic the jet from the Crab Nebula, the laboratory experiment requires magnetic fields that have the right properties. So the fields must have a strong azimuthal or toroidal component, which is generated near the target where the jet is launched, which is to say that that's the field that's sort of going around the perimeter of the jet. And then the fields must be embedded or frozen in so that they can be advected with the fast-moving magnetized plasma flow. And the pointing flux, which is essentially the energy carried by the fields, has to dominate near the jet launch point rather than the energy that's carried by the particles. And our laser-produced experiments can produce jets that meet these requirements. So they will have a higher plasma temperature, and a factor of 10 faster flow velocity and large magnetic Reynolds number, which leads to good frozen-in conditions and magnetic field advection so that we can really match these conditions that are present in the Crab Nebula. So this slide here is kind of packed with data and shows sort of the whole story of what's going on. So up in the top left is a cartoon diagram of the experiment where there's sort of a cone-shaped target that's illuminated by these 1 kilojoule laser pulses. And then those produce sort of these gray plasma bubbles, which have circulating magnetic fields, and then launch a plasma jet sort of out of the cone. And then we measure the magnetic fields that are produced here using proton radiography, monoenergetic proton radiography, where protons of a single energy are propagated through the experiment. And then by interacting with the fields there, we can take an image of where they end up essentially. And because the position on the screen is proportional to the magnetic field that they experience as they pass through the experiment, we can have some idea of what's going on with the magnetic fields. And you can see a couple of proton radiographs at the right of sort of different time steps where you notice that there is sort of the same kind of clumping and directional changes going on that we observed in the X-ray images of the Crab Nebula jet. And we can see that this clumping and wiggling, essentially they result from these MHD current-driven instabilities for which the most unstable modes are shown down in the bottom right. There's the M = 0 or sausage mode, and then the M = 1 or kink mode. And these unstable kink modes have a growth rate that's comparable to the inverse of the time required for the phase velocity of an Alfvén wave to cross the jet column. You can see the expression there with the Alfvén velocity over the radius of the jet gives a growth rate of about 3 × 10⁹ per second. And we can kind of confirm that those results are due to the MHD kink instabilities by having sort of this similar experiment here, where instead of a cone-shaped target, lasers were fired at a flat target. And the difference between them here is that in this case, the jet is farther away from the center of these plasma bubbles. So the toroidal field is weaker there. And when the toroidal field is weaker near the origin of the jet, essentially they're too weak to destabilize the flow of the jet. So we don't see the same kind of bunching and clumping up and wiggling of the jet that we do where the toroidal fields are stronger, which indicates that those results were in fact the result of the MHD instabilities. So we can justify the relevance of this experiment to the Crab Nebula jet by sort of examining the magnetization parameter, which is basically the extent to which the energy is carried by the Poynting flux as opposed to the particles. So in both the Crab Nebula as well as this experiment, the magnetization parameter is greater than 1 where the jet is launched, which is to say the Poynting flux dominates and is very small sort of at the jet front, which is where the particles dominate. So we can match that condition quite well here. And then, so yeah, the figures here on the left is that X-ray image again, and then on the right is a simulation of this experiment. And then this is table here is just showing sort of some of the same kind of things that were in the previous collisionless shock experiment. So the sort of similarity scaling between the lab jet and the Crab Nebula jet. Where we can see that the temperatures, the density, and the radius are quite different, along with the time scales and the magnetic field, but that these sort of dimensionless parameters here are large in both the Omega experiment as well as in the astrophysical environment, which allows us to use that sort of scale invariance of the MHD fluid equations that we talked about before. So in order to scale the laboratory results to the environment of the Crab Nebula, the MHD equations need to be invariant under a transformation for the two systems. So this is just showing that in order to sort of scale the results to be understandable, we have to take the size in the lab and scale that to the size in the sky, as well as the density and the pressure. So these are just sort of the parameters that allow us to do that, and then the way that they scale the other quantities that are relevant to the experiment. And then this here is just sort of demonstrating that we are able to scale those correctly so that for example, the jet velocity, the time scale of evolution, and the magnetic field are comparable between the scaled laboratory experiment and the astrophysical system, which provides validation that the results that we see here are relevant to the Crab Nebula jet. And then I will be changing gears now to talk about the investigation of fast magnetic reconnection at omega. So magnetic reconnection is a ubiquitous phenomenon which appears in sort of many different areas of astrophysics. It's the process by which magnetic fields change their topology and release energy, as we can see from this cartoon here, where there's sort of these oppositely directed magnetic fields that are driven together by plasma flow. And then at the center, something happens where they essentially break the topology that they're originally in, and then they come out sort of off to the side here and release energy when they do that. It's an important phenomenon in sort of a bunch of things that you can have these pretty pictures of, like the Earth's magnetosphere, where it's proposed as being an important part of generating aurora events, as well as solar flares, which is sort of the kind of hallmark context which magnetic reconnection is discussed in. And it's also important in the supernovae and their remnants. So in fact, it has relevance to the astrophysical jets that we talked about in the previous section, as well as more exotic environments like magnetars, which are neutron stars that have extremely strong magnetic fields. And it can be explored in a variety of different experimental configurations, each of which explores potentially different parameter regimes. So the first is sort of these magnetically driven experiments where you can have a plasma that is strongly controlled by the magnetic fields as opposed to its own thermal pressure. Or laser-driven experiments where you can generate a system where the opposite is true and the thermal pressure sort of dominates the magnetic pressure. Or pulse power experiments where they are sort of comparable in the sense that there's this parameter of the plasma beta, which is the ratio of the thermal pressure to the magnetic pressure. And in these pulse power experiments, that can be near 1. So sort of a theoretical overview of why we might care about this. The classical Sweet-Parker reconnection model cannot explain the fast reconnections that we observe in solar flares. So the Sweet-Parker model is sort of the earliest and simplest model for magnetic reconnection. It considers a two-dimensional picture with a very long, very thin current sheet, and I'll show what that means on the next slide, which is in steady state. And it has a very long time scale prediction for the rate at which these fields are reconnected and the energy is released. So the Sweet-Parker model suggests that a reconnection in a solar flare-like system might take place over 10 days, whereas we observe that they take place over the course of about 30 minutes, which is a huge discrepancy between the theoretical model and our observation. And the parameter that ends up being really important to sort of all these reconnection discussions is this Lundquist number, S, which is sort of a characteristic length scale multiplied by the Alfvén speed divided by the magnetic diffusivity. And then that's it tends to be quite large, which is why the Sweet-Parker model, which predicts a time scale that scales with the square root of the Lundquist number, is too long, essentially. So this cartoon is showing basically the picture of what is going on in the Sweet-Parker model. So sort of as before, we have these initially oppositely directed magnetic fields, which are labeled B in, and then they're pushed into the center of the region with this inflowing plasma, where they reconnect in this, the gray box, which is representing the thin current sheet. And then they are advected out with the plasma. And then from dimensional and scaling arguments, resistive MHD equations led Sweet and Parker to conclude that this outflow velocity is essentially the Alfvén speed. And then the inflow velocity is much slower than that. It's the Alfvén speed divided by the Lundquist number to the 1/2. And that the width of the current sheet as compared to its length is also scaled by this Lundquist number to the -1/2. And then based on those inflow and outflow measurements, the Sweet-Parker model predicts a very long time scale for reconnection, which scales as the Lundquist number to the 1/2. And in most systems, the Lundquist number is much larger than 1. So for astrophysical plasmas like the solar wind, the Lundquist number can be as high as 10 to the 9 to 10 to the 20, which is just extremely high. And it's actually very difficult to reproduce in the laboratory, but we can get high Lundquist numbers on the order of 10 to the 2 to 10 to the 4. So the Sweet-Parker model obviously doesn't tell the whole story. As I mentioned before, solar reconnection events take place on the timescale of hours and not months. So this is sort of resolved in theory by invoking the plasma tearing instability, which says that at high Lundquist number, current sheets are unstable to the tearing instability and might split into isolated magnetic islands, which results in an enhanced reconnection rate, which is shown in this cartoon here. So initially we have sort of this Sweet-Parker-like configuration with a long, thin current sheet. And then as it thins out, the Lundquist number increases. And when the Lundquist number gets high enough, the current sheet breaks up into multiple isolated current sheets, sort of separated by these magnetic islands, which are called plasmoids. And again, just for some reference of the scale here, the Lundquist number is really high in astrophysical plasmas. So we expect this to be the relevant process there. And we would like to investigate that in our laboratory plasmas, which have lower but still high Lundquist numbers. So the prediction of the theory is that these plasmoids form on a timescale which is much faster than Sweet-Parker reconnection. Basically, the stable current sheet never forms, but the important thing is that that really enhances the reconnection rate, which might allow us to explain the faster reconnection that we observe in astrophysical contexts. And although these plasmoids and the tearing instability are common in simulations, they've proven difficult to experimentally observe historically. So the experiment that we're going to talk about here is shown on this slide, where W.Fox and his team investigated the onset of the tearing instability in a laser-driven magnetic reconnection experiment at the Omega Laser Facility. So you can see on the left, it's sort of a busy diagram, but there are these two sort of square targets that are illuminated with these 1.2 kilojoule, 351 nanometer laser drive beams, and it produces these these plasma bubbles, which have circulating magnetic fields. And then as those bubbles expand, those magnetic fields are pushed into each other. And in that little green oval there, they undergo magnetic reconnection. And they were imaged with proton radiography, the same diagnostic that I mentioned before, where you have some proton source that produces charged particles that propagate through there, which are deflected by the magnetic fields and are collected. So you can see what the magnetic fields were like. And this experiment generated a plasma with high beta, so a high ratio of thermal pressure to magnetic pressure, and achieved a Lundquist number in this sort of 2,500 to 4,500 range. So not as large as astrophysical systems, but still pretty large. And this parameter space is investigation into a particular regime of reconnection. So basically, the theory predicts that there are different scaling rules and different physics that dominate depending on what range of beta and what Lundquist number you're at. And by exploring that in this experiment, we're able to provide validation for those theories. So this slide here is showing the proton radiographs and then some of the recovered results from those radiographs. So on the left are the raw radiographs themselves, where darker corresponds to higher proton fluence. You can see the time evolution of how the protons are being deflected there. And I guess sort of the basic intuition one should have when looking at these is that a region that is brighter should have a higher field because more of the protons are getting pushed out of there. So it must be a higher field there to push them away from that region. And you can sort of do better than that with these sophisticated reconstruction algorithms, which allow for the recovery of sort of the path integrated field that the particles experience as they propagate through the plasma. Which is shown, that's what's shown on the right there, the reconstructions at two different time steps. So the top panel, which is the one that's sort of like divided into red and blue at each time step, is the field. And then the one below that on each part is the current, which is just recovered by taking the curl of the path integrated field. So you can see at the early times, we have sort of this long, thin current sheet that we described before. That breaks up later on, sort of as a result of those tearing modes. And the evolution of the current sheet, shows a breakup with time as a result of the tearing instability. And so measurements of the magnetic field give insight into the growth rate of the instability, which is sort of how we can try to get validation of these theories. So shown on the left here is their lineouts sort of all taken along the current sheet. where you can see variations in the proton fluence, as well as in the current itself. And then, so different plasmoid theories have different predictions for what the fastest growing modes of the tearing instability are. And this kind of measurement can sort of let you estimate that for this experiment. And so these experiments, such as this one, they help provide validation for the different theoretical predictions and astrophysical contexts they may be appropriate to use in. So basically, they allow us to discriminate between sort of different theoretical predictions that we have for this sort of complicated phenomenon that is difficult to investigate in space, but we can investigate in the laboratory. So summary, laboratory astrophysics is the study of astrophysical objects in the laboratory. With control over initial conditions and improved instruments, researchers can better explore the physics behind an astrophysical system. Laboratory astrophysics is enabled by scale invariance of the plasma fluid equations in the correct regime. And in this presentation, we've seen how laboratory astrophysics can let us study the physics of collisionless shocks, create conditions similar to the center of the sun, or learn why the Crab Nebula jet has kinking behavior, and to explore fast magnetic reconnection.